Welcome, everybody. My name is Adrian Correndo. I am an agronomy PhD student at the Department of Agronomy of Kansas State University. Today's video is in regards to a new data code that we published on the Harvard Dataverse repository related to agro-meteorological data using our software, as you can see on the screen I'm sharing right now. And this code is part of the data curation process that we use to apply many of our research projects on the Doctors in PD's lab at the Department of Agronomy of K-State. So, as many of you may be aware, many times it happens that we don't have access to weather data or to a weather station at specific locations for which we need some weather variables for research purposes or for making crop management decisions. So in those cases, we may still get access to web data through what is known as API client sources. And in this case, we are going to show you a tutorial of how to do it using our software. So in this on this screen, you are seeing the web page where the data set is published. The link is provided on the description of the video. You may see it there. Um, and the data set consists on four main files. One file is the code itself, of course, and then we have two data tables that they are um, providing examples of the inputs that the user needs to specify in order to retrieve the weather data. Finally, we are also including a tutorial in a PDF document where you can find all the details of and explanations about the code and the different equations we are we are using during the code. Okay, so for this code, we're using three main databases that develop API client sources in our software. One of them is Daimet. Again, these links will be provided on the description of the video. You can find here all the details about this library in R. We are also using NASA Power as an alternative API source, and we are also using API for chirps, okay, that provides us data on precipitation. Here you will find all the details in terms of geographical coverage and spatial temporal resolution of each of the sources. Okay, so we may get access to the four files of the repository. You just need to select them. I'm going to download, and you can ask for a zip file. Let's see. Let's wait for a minute. Let's try again. For using this data set, you don't need to have any account on the repository because they are of public access. So it should be fine if you just get the link. Okay, something is not working here. Let me try again with the files. Let's refresh. We'll select the files, go to download, and then we are supposed to get them here. We're getting a zip file. We downloaded it. Okay, let's go to the folder containing the files. As you can see, I have already downloaded before, so we may delete that version, and we just open the zip file, and then we'll extract the files to the desktop. Let's create a let's create a new folder, and we'll call weather code, and then we simply extract the files there. Now let's go to the desktop. We open that folder containing the files, and here you have the PDF with the tutorial, the two data tables, and the code itself. Let's open the tutorial to show you very briefly the structure of the document. You will find here our names, our contacts, if you need any further help or you have any additional question. We are providing an introduction describing all the sources and what the code is doing. And from sections 2 to 5, we are detailing all the different functions and equations we are using when we are retrieving the data or processing the data to getting summaries in terms of the cropping season or historical weather. And finally, we are providing references um, for all the citations we are using for this. So let me describe very briefly the three data sources. They met is probably the best source in terms of number of variables and the spatial the resolution. In terms of temporal resolution, they all have daily weather, and that is very nice. But the limitation of the med is mainly that it's only available for North America, including Canada, United States, and Mexico. So if you are outside of this region, you will need to use some of these other sources, NASA Power chips. Both are um, covering at a global scale, also at daily resolution, but with different spatial resolution. NASA Power with about 50 kilometers and chips with 5 kilometers, much better. In terms of number of variables, NASA Power provides the precipitations, relative humidity, temperature variables, radiation as well, while CHIRPS only provides precipitation data, but at a much better resolution, as you can see here in the table. And here you have the links for the documentation of each of the libraries, and then we start with the explanations of the code itself. So let's go to the code file. Now we open here the code. See, let's maximize. Okay. Here you have a kind of table of contents where you can go to the different sections of the code. As you may see here, it's not the traditional R script format, but it's R Markdown format instead. Under this type of documents, we are able to organize our code in what they call chunks, that they are just small windows or pieces of the code where we can get a much neat um, code. Okay, so for example, here then in the first chunk we have all the libraries that we need to install and load before running the code. We have the details what each of the packages is intended for. And then we are providing a chunk if the user wants to create the input of the locations he's interested in our software. He can use this piece of code is what we use to create the files. The two files that you will find, example input and example input historical. Um, and here, the most important part probably is where we are reading the files containing the inputs of the user. So this code is automatically um, identifying the working directory we are in no matter if you're in the desktop or in whatever folder you want. And the user just need to take care about providing the right name of the file. In this case, if we're interested in seasonal weather during the cropping seasons, we will use this Excel file in a CSV format. So we can load it here, as you can see, and this is how the table should look like. Okay, we will have each of the rows, it will correspond to one site at a time, and then the different columns are the different variables or metadata that we need to provide as inputs. In this case, we are providing a unique ID, then which crop is for the weather, and then we have the name of the site, latitude and longitude, the most important, to um, to make the request for the weather data, and then we are providing different dates, and the user at least needs to provide a start and an end date for determining the period for which he wants to retrieve weather data. Okay. Uh, Very similarly, if we are interested on historical weather instead of single seasons, here is exactly the same, but we are providing a start date of, in this case, in the year 2000, and then we are also um, um, adding the request until the end of 2019. So we are getting the last 20 years of weather data. So now let's go to the retrieving and processing data section. Here we are providing a brief explanation that the user will need to read before running the chunks. This chunk is also important to run because we are establishing some constant to run the equations later. In this case, for estimating the reference evapotranspiration, because it's not a default variable in any of the libraries, neither NASA Power or DayMet, but we may still use the Hargreaves and Samani approach to estimate it using radiation. You will see the details of the equation in the tutorial. So for retrieving the weather data, for example, using DayMet, we may just need to run this chunk containing the function that is called weather.daymet. And here there are all the details of all the equations and different data wrangling that we are doing. So basically this function is creating a data frame containing the weather data using DayMet. So on the next chunk, the user will run the weather data function. Let's write as an example. As you can see here, we have the function already on the environment. So we just need to call the function, and user, if you see, the user needs to provide the input, which is the name of the data frame containing the input data, in this case for seasonal. And if the user is interested on retrieving data before the starting date, that it could be normally planting date, it can provide this definition of DPP, which means days prior planting. By default is 0, but if user is interested in, for example, in retrieving weather data 60 days before planting, it will just add a 60 there and it will be all set. And this is defining a data frame, as we can see below, is defining this data frame containing the weather of the image. So let's run the function, and then we are getting all the weather. Okay. So here we can see the format of the table, and we are exporting it to a CSV format as well. So we have all the metadata columns that we provided at the beginning, and then we have for each of the rows, we have each day of the year for which we requested the data. By the end of the table, you'll find the columns having the day length, precipitation, radiation, etc. So very similarly, the NASA power function, if we are interested on using this, we'll just run this chunk containing the function for NASA Power, and then we will create a data frame using the NASA Power source, running this chunk using this exactly the same format as before. The user need to call the function, and inside the function need to uh, provide the name of the of the data frame containing the input data, and then if interested using the DPP as the prior planting. And here again we have the table containing the weather using NASA Power. And finally we also have chirps. Again we run the function, and then we run the request with the weather.chirps function. Exactly with the same format. User needs to uh, specify the input data, and then use DPP if he's interested on that feature. So as you can see here, for the chirps database, we are only getting precipitations, and then the package is also providing other indices related to distribution of precipitation. You can check on the CHIPS documentation for more details. Well, now we will jump to the section of creating time intervals to create summaries of the weather data. So let's suppose that we are in a specific cropping season for each of the locations, and we want to get a summary of the whole cropping season. Or we call it full season interval. So here we just defining a time frame from the start to the end. Let's say that is planting day to maturity, and then we are making a summary of variables, let's say mean temperature, accumulated precipitations, etc., and diversity of distribution of precipitations, extreme temperature event. You can see the examples on the documentation. um, User may also have another option, which is creating even intervals within the season. Let's say that we want to create 4 periods from planting to maturity, and we will divide the, the season in 4 periods of equal number of days. And again, if user is interested in days prior to planting, he just need to provide the number of days he's using for the weather data again. So let's see the example. We are creating 5 periods, the previous of planting, and then from planting to maturity, we're creating 4 periods with the same number of days from, and here we have the starting and the end date of each of the intervals. And lastly, we also added the option of using custom intervals if user is interested on using phenological dates. For example, let's say in the input example 5, you will find 4 dates. A start, that means planting; flow, that means flowering; C5, that means seed filling; and then end as maturity. So we will create different periods uh, using those reference dates as end or starting points for each of the intervals. So let's run this chunk, and then as you can see here, you are creating periods from previous to planting, planting to flowering, flowering to seed filling, seed filling to maturity. And then we'll have a start and end of each of the intervals. And we'll have that for each of the locations. So for running the summaries again, the user may need to run this chunk, which creates a function to create a summary for either they made on NASA Power, because in purpose we made them with the same variables and with the same names. So you can run the same function for either of them. Here you have all the variables we are creating, the duration of the period, mean temperature, radiation, BPD, reference, evapotranspiration, growing degree days, etc. And then we also can create a summary function for chirps. Finally, we may create a summary, and in this case, here we call the function summary.dimed or NASA power, and then user again needs to specify where is the data frame, the name of the data frame containing in this case the weather data. That's the second step, and then the user needs to specify which type of seasonal interval he wants. So for example, here we're using custom, but we also have the season option or the event option. So let's keep using the custom function, and here we will see the table that we created. In this case, let's see, for example, from planting to flowering, in the first location we are having 80 days for this period, and we have 198 millimeters of precipitation with 20.8 as mean temperature in Celsius degrees, etc. And you have that for all the different variables we have created. Exactly the same, we have the summary for NASA Power as well. Here we created the summary, and then for the chips, we also create a summary that quick. And now we have the section that includes the possibility of using historical weather to, it could be for simulation, crop simulation purposes. So we will use this exactly the same function, weather.dimed, for using dimed, for example, and use it again, just need to specify the input. So where is the data containing the historical metadata to make the proper request. And here we are creating a data frame called hist.weather.dimed. We just run the function, and then we are getting the daily weather for the historical period we are. Let's say sometimes it could happen that we have a problem with the package. Let's see. Running again. Connection timeout. Probably the server is down. Sometimes it happens. So let's try with NASA Power now. That could happen. Don't worry. It could happen that some of the servers, the API clients, are down for a while. And then the code may send you this type of error. Let's wait for a minute. It could take a while depending on the number of locations. You see the NASA Power is working well now. So no issue for that. When you have this type of error that say timeout was reached, it means that you are making the request to the server, but the server for some reason is not working right now. So you may just wait for a while and then try again later. So let's run again and then wait. Let's see. It's good that this happened because we may show all the different issues that we may face. Okay, it's not working right now, but we may try it later. So let's try with chirps. It should work well. Let's see. It could happen that also the chip server is not working now. Oh, it's taking a while. It could be the internet. You see now it worked. So let's see the example. You have the function here to view. Uh, you see we are getting the precipitation for each of the days. The summaries, don't worry about this because it's for by period, so it's okay. So it worked okay. So we are getting the daily precipitation from 2000 to 2019. It should be here, sorry. 2019, you see, is the maximum date, and we are getting for each of the days of the period, we are getting the precipitation. So then we may create a summary. So for creating the intervals functions, we may run this. That is the functions to create summaries by years or by year months. And then we may specify, we don't use the day method right now because it wasn't working the server. So we may create a summary. Let's go with NASA Power. So we need to run this. We may create year or year months from the NASA Power data. We need to specify where is the historical data set. So the code, the function will know the data set we are working with, and then it will create the periods depending on the dates we ask the request. And here, for example, we are creating the summary for the email on NASA Power is the same. In this case, it will be for NASA Power, and the user just need to specify the input here, historical weather, and then the type of interval, so in terms of historical data. So it could be years or year months, you see, whatever option you want. So let's try with years and then with year months. You see here we're having the summary for each of the years of the period. And similarly, if we specify year months, we just add year months there, and then we'll run the code again. We will get the same summary, but by month. You see here we have the year 2000 from January, February, March, etc. And then we have all the summary variables for each of those months. Okay, we are okay, and then let's try with chirps. Okay, we created videos by years, so all work well. So that's all I had for today. Let's try once more with the NASA Power Historical. I'm curious what's going on with this code, but it seems that the server is not working. Let's see, let's see. Okay, sometime something's going on with the server, so we may try later with this. Let me know if you have any issues. But that's all I had in terms of the code for today. So thank you very much for attending this video, and I hope to see you soon in the next tutorial. So stay tuned for new updates.